Okay, good afternoon, everyone. This is live stream number 10 of 10. It's been quite a journey. Hope you've enjoyed them, and I really hope that they've been useful to you and that they'll continue to be useful to you. Okay, so welcome to all of you. It's great to have you with us. This live stream is being presented by SIMI, the Shai Zibalo Maths Institute. And just a quick reminder for anyone who might be watching the first of these. Basically, the way we've worked them is that each day there's a set of questions, and these are the questions that we work through, 10 topics that we've covered across both papers, paper 1 and paper 2. All the resources, the questions are available at simi.education, and each day as the live stream finishes, we upload the worked solutions for that live stream. The videos remain available after the fact on YouTube, and the links are all available on the SIMI website. So we hope that this is going to be a useful resource, not only for the matrics of 2023, but indeed for people going forward. If you found them helpful, please like, share, and subscribe. Tell your friends, tell your grade 11 friends. A lot of it is grade 11 work, as you would know. Right, so we're going to dive in, and as we've done each time, we're going to just start off by looking at kind of what are the formulae that we get given. And for data handling, there are just the two, and they are, the first one tells us how to find the mean of some group data, and we'll look at that. And the second formula is a formula for variance, which, as we know, is the square of standard deviation. There's some other stuff that I really strongly recommend that you know, right? And I probably haven't included all of it, but just some stuff that I think is really kind of important, and that is that our first quartile, all right, is this little formula that we don't get given. You add 1 to n, the number of data items, and you divide by 4. That gives you the position of the first quartile in a ranked list. The median, the second quartile, we double that number, and the third quartile, we triple that number. That gives us the position, not the actual quartile, but the position of the quartile. Right. If it turns out that the quartile falls between two numbers, in other words, we get, say, 17,5 for the 17,5th position, then we just average the numbers in the 17th and the 18th position. Okay. Interquartile range is third quartile minus first quartile. And then the 5-number summary, really important idea, is the smallest, the first quartile, the second quartile, the third quartile, and the biggest. All right. And then we use all of that data to plot box and whisker plots. And remember, the first whisker starts at the minimum value. The box starts in quartile 1. There's a median, which is the line in the middle of the box, quartile 2, and quartile 3 is the right-hand end of the box, and then the maximum value is the end of the right-hand whisker. Just a little bit about symmetry or skewness. All right. There's the definitions. Negatively skewed or skewed left, you need to know both of those, is when, and now just listen carefully to this, it's not about there being more data below the median. That's absolute nonsense. There's an equal amount of data, an equal number of data points on either side of the median, always. That's what the median is, right? But data that's skewed left or negatively skewed, the data that's less than the median is more spread out than the data that's bigger than the median. Okay, and positively skewed the other way around. Positively skewed, the data above the median, bigger than the median, is more spread out than the data below the median. Okay, right. I'm going to just dive in and just show you two. Sorry, that's not what I wanted to show you. I wanted to show you this. Right, I actually had it right the first time. There it is. Okay, I want to talk a little bit about bivariate data, which is a matric topic in particular. And so what we've got here, we've got some data points, right? You can see them, the 5 or 6, 4 of them, in fact, different colors. Okay, and the reason this thing is called a least squares regression line, each data point, if we work out how far it is from the line, okay, so in other words, here, this one's above the line, this one's below the line, above the line, below the line, above the line. And now what we do is we square those numbers. And the reason we square them is because if we didn't square them, then the ones that are above would actually cancel out with the ones that are below. A very similar idea happens when we work out our standard deviation. All right, and the least squares regression line is actually the line that minimizes the sum of the areas of all those squares. So at the moment, in this particular sketch, the sum of the squares is 15,7. Okay, I'm going to drag this line around and see, you can see what happens. All right, so that is not as good a line of best fit, or least squares regression line. All right, 13, yeah, it seems to be able to get to about 13,06. Now, I just want to show you, there's a thing called the centroid, and the centroid is the average of the x values and the average of the y values. Your least squares regression line, the least squares regression line, which is a calculated line of best fit, will always go through that centroid, that point there. So if I show it, you'll see I'm actually quite close. Notice if I go and drag the endpoints of these here onto the least squares regression line, you'll notice two things. One is that my sum of my squares is going to drop, all right, and also you'll notice that at that point it will then go through the the mean of x and mean of y, what we call the centroid. But really important, the least squares regression line always goes through the line of always goes through the x bar y bar point. Okay. The other little sketch that I want to show you is just the kind of the influence of outliers. All right, what happens when we have an outlier? So I'm going to show you this red point. I'm actually dragging it. I'm going to sort of drag some of these points like this and this and this and this. All right. Yeah. Okay. And in fact, the red point is somewhat of an outlier. Okay. I actually can, let me just drag this point over here without the line of best fit. Okay. I think you can now see that the red point is something of an outlier. Okay. If I show the line of best fit for all the points, right, there it is there. Okay. And that red point is actually kind of messing things up completely. And if I show the correlation of all the points, it's actually very low. All right. However, what I'm going to do now is I'm going to show the line of best fit without the red point. Okay. And you'll see it's actually a very nice line of best fit. And the correlation coefficient is going to be very strong, very close to 1. Sorry, that's of all points. Without the red point, it's going to be like 0.99. Okay. So what we can see is that if we've got, I'm just going to turn these off and I'm just going to rearrange some of these points. All right. If we have an outlier, okay, and I'm just this time I'm going to move the outlier up here somewhere. All right. If we have an outlier, what will happen is that if we remove the outlier, we get a stronger correlation. So there's a correlation with that outlier, and there's a correlation without it. In terms of the line of best fit, that's the line of best fit of all points. A question, an interpretation question is, what would happen to the line of best fit if I excluded the red point? Well, if you think about it, that red point's actually pulling the line. It's not mathematically, it's not a mathematical term. It's actually sort of almost pulling the line up. The gradient will get much steeper. Notice it's got a negative gradient. If I show the line of best fit without the red data point, notice that the gradient has actually got steeper. The gradients increase. Okay. And that I hope will help you with solving, answering some sort of interpretation questions. Okay, we're going to dive into actually answering some questions now. And here we go. We're just going to find our actual questions. There they are. All right. First question. When a rugby player is substituted, the average weight of the 8 players in the scrum drops by 2 kilograms. Okay. So now, basically, what has happened is if we think about the weight of the rugby players initially, suppose it was T for total weight, and we divide by 8, all right, we get some value, okay? But when we replace the player and we divide by 8, all right, with the sort of the new weight, total weight number 2, this here is actually 2 kilograms less. Right. So if we now multiply this, so this is the total weight divided by 8, the total weight divided by 2. Right. If we now multiply through here by 8, we actually get the total weight equals total weight 1 is total weight 2 minus 16. Right. So the player who changed actually weighed 16 kilograms less. Okay. All right. I hope that makes sense. Yeah. Right. Next question. Find to 3 decimal places the standard deviation of the following numbers without using a calculator. Now, remember we get given this formula. All right. And the formula that we get given, it's a really cool formula because it actually has 2 sigmas in. There are 2 sigmas that we use in mathematics. This is a capital Greek S and it means sum, right? And this is a little Greek S and it's for standard deviation. When it's squared, it's actually the variance. Now the formula looks like this. And what it's basically saying is take every single data item, subtract the mean, square the result, and then add them all up. All right. And then divide by how many there are. So in this case, the formula's got an n in it, but in this case, it's going to be 4. All right. And that will give you your variance. Now, the reason that we square, it's exactly what I was talking about with the least squares regression line. The reason that we square the differences is so that we don't get a cancelling out of numbers that are bigger than the mean by a certain amount and others that are smaller. Okay, so let's have a look. So what we're going to do here, we're going to first work out the mean, all right? And the mean of all these numbers, you just add them all up and divide by how many there are. It's just 7. Then we're going to take every single term and we're going to minus the mean. We're going to square the result. Square the result. We're going to square the result. And lastly, we're going to take 13 minus 7, and we're going to square the result. Sometimes in an exam, you get given a kind of a table to sort of help you with your layout here. All right, we're going to add all of those up, and we're going to divide by 4. All right, when we do that, in this particular example, we actually get 66 over 4. 66 over 4. And that is not the standard deviation. That is, in fact, the variance. So our standard deviation will be the square root of 66 over 4. I've kind of put some numbers into my calculator already in preparation for this session just to save some time. So I don't want to override that data to show you that this answer is in fact correct. Okay. Right. So 4,062. Obviously, you can check it with a calculator, and in an exam, I'd strongly recommend that you do. Okay, question number 3. Tobo has got an average of 78% for his 5 maths tests so far this term. What mark must he get on his 6th and final test for his average mark to be an A? All right, this is basic average stuff, all right? But obviously, what we know is that his total number of marks so far, when we divide that by 5, we get 78. Right. That actually means that so far, all his tests added together is 5 times 78, which is 390. All right. Now, what we need, this is what he's kind of got. What we need is for the new total, all right, with the last test in, to divide by 6 and give us an average of 80 to get an A. I'm sure you guys have done these calculations for yourself, all right? And so the new total actually needs to be 480. And the only mark that's going to contribute to that new total is the last test. So in fact, on the last test, he needs to get at least, obviously he can get more, but he needs to get at least 90% to go from 390 to 480. Okay. Right, question number 4. Okay, so what we've got here, we've got a whole lot of data represented in a stem and leaf diagram. Really important that we know how these work. Basically, one of our first number is 33, then 38, etc. First thing is the range. The range is just the biggest number, which is 76, minus the smallest number, which is 33, and we get a range of 43. The mean. Okay, now what I've done is I've put these numbers into my calculator already, as I said, just in preparation, just to save some time. Okay, sorry. It's like screen. Okay, here we go. So I'm going to go Shift Stat 4 for the variables about this data. I've put the data in already. And basically, there are three things that I'm interested in. How many data items are there? Okay, I've got that already. That's we could check that, but I'm not going to bother to check it. Right, then the mean. So I'm going to go number 2. Just be careful. You've actually got to press equals to get the answer. And we get 53,19. That's the mean of that data. Be mindful when you put the data into your calculator. Don't rush, all right? Because obviously all your other answers are now going to kind of depend on that data. So take your time. All right, now go Shift Stat. Again, I'm going to go for the variables about this data, and I'm going to go for option 3, which is my standard deviation. Don't forget, it's not on screen yet. That's still the mean. I've got to press equals, and I get 10,01. But the mode is the most frequently occurring item. And in fact, it seems to me that 43 actually occurs the most times. So the mode is actually going to be 43. Right, now we're going to work out the 5-number summary. And for that, we're going to use that little formula that I put up earlier, n plus 1 over 4. Right, now this particular one, there are 27 data points. So 27 plus 1 over 4, 28 over 4, it's actually 7. So my first quartile will be, okay, first number is going to be my minimum number. And remember, my minimum number was 33. My maximum was 76. And in between here, I'm going to put the quartiles. The quartiles are going to be in 7th place, 14th place, and 21st place. So 7th place, 1, 2, 3, 4, 5, 6, 7. 43 is my first quartile. My second quartile, also referred to as my median, all right, is going to be in 14th place. Okay, and if I count that up, you'll get 55. And then my third quartile in 21st place, and that is 59. That's what we call the 5-number summary. We just put the numbers down, separating them by semicolons. The interquartile range, remember, is your third quartile minus your first quartile. It's a measure of the spread of the middle 50% of your data. So we can chop off the last quarter and the smallest quarter and the biggest quarter, and it's just a measure of spread of the middle 50%. Okay, and obviously in this case, 53 at the IQR, the interquartile range, is just going to be 59 minus 43, which is 16. Okay, and then it says, they give us here a definition of what an outlier is. An outlier is deemed to be a data value which is more than 1.5 times the interquartile range, above the third quartile, or more than 1.5 times the interquartile range below the first quartile. Okay, so now they've asked us to check, does this data set have any outliers? Well, 1.5 times my interquartile range, 1.5 times 16, 1.5 is 24. So I'm basically, for something to be an outlier, it needs to be 24 bigger than 59. So it would need to be bigger than 93, bigger than 93, or it must be more than 24 below this number here. All right, so 43 minus 24, that's actually 19. So it would need to be bigger than 93 or smaller than 19. And in fact, remember our minimum value here was 33 and our biggest was 76. So this data set has no outliers. Okay, the next thing we got to do here is to draw our box and whisker. 33 is 31, 32, 33, that's going to be the end of our whisker. Then 43, 41, 42, 43 is going to be the start of our box. I'm not doing this very accurately, that the memo online will be more accurate. 1, 2, 3, 4, 5, 55. 59 is kind of just over here somewhere. And then 76 is 1, 2, 3, 4, 5, 6, somewhere over here. Okay, so my box and whisker in the exam, rather use a ruler. Okay, my box and whisker is going to look something like that. Right. The next question, in fact, it doesn't ask. Okay, it actually doesn't ask. But just to, while we're here, let's just talk about the symmetry of this. This one is skewed to the left. All right. Or, and I always remember this because I'm left-handed, and I get a little bit grumpy with the fact that left is to be considered like negative. Okay, that's how I remember it. Negatively skewed. Okay, positive, right, left, negative. Okay, so, and the reason being is that the data less than the median is more spread out than the data. So this is the reason I haven't asked about skewness here, is that this is a problematic one to discuss skewness on. We're not going to talk about skewness on this particular one. We're going to dive straight into the next question, all right, which actually asks us to describe the skewness of each of these. Okay, right. A good exam question will make it completely clear, and you shouldn't get a kind of contradiction depending on whether you look at the whiskers or the position of the median in the box. This one is clearly skewed to the right. Right, or positively skewed. One, pretty symmetrical. Sorry, not the next one is not symmetrical at all. The last one is pretty symmetrical. All right. And the middle one is in fact skewed to the left, negatively skewed. Yeah. What it means, just a reminder, to be sort of skewed left or negatively skewed, the data less than the median is more spread out than the data bigger than the median. There's not more data. There's the same amount of data either side of the median. It's about the spread. Okay, and where that spread is biggest. Right, now the next question that we're going to look at is question number 6. And it's a question around grouped data. Okay, and this first now asks, what's the modal group? What's the group that's kind of the most common? And we can see that it's actually 65 to 75. Add all these numbers up, okay, we actually get, we have to quickly do that, 4, 8, 22, 32, 45, 57, 70, 80. There are 80 numbers, yeah? All right. So the median will be kind of the 40th number. And here there's 1, 4, 8, 22, 32, 45. All right. So the median will in fact be in this group from 85 to 95, because that's there's only 32 numbers before that group, and after that group there's 45. So 85 to 95 is the group, the group or the class in which the median will lie. The first quartile, remember, will be in the kind of the 20th position, a quarter of 80. All right, 1, 4, 8, 22. So the first quartile will in fact lie in box in the group from 65 to 75. The third quartile will be in kind of 3 times 20, like position number 60. All right, 1, 4, 8, 22, 32, 45, 57, 70. So in fact, in the 105 to 115. Right, then it asks us to determine an estimate for the mean. Okay, now this is where this little formula comes in. And what it says is that the mean is going to be the sum of the frequencies times the x value over n. Right. Now, we don't know for these points here, for this group. Let's just look at this one here. Even this first one. This one instance in this group, we don't know if it was 35 or in fact 44 and a half or what it was. So what we do now is we use the midpoints, all right? And we're going to assume that this one person actually was on the midpoint of 40, that these three people, marks, whatever they were, these three instances, averaged out at 50, all right? And these four at 60. Now, at this stage, I'm going to show you how to put your calculator into frequency mode. And in fact, I actually like to keep mine in that mode. So screen again, all the time. It looks something like this. Okay, what we're going to do, we're going to press all clear. We're going to go shift mode, press the down arrow, and you'll see option 3 talks about stat. And here I can turn on frequency. So I'm going to turn on frequency, and in fact, I'll just leave it on. I wanted to show you how to turn it on, but there it is. Now I'm going to go into mode stat, and this is still one variable stats, okay? And now you'll see I've got a frequency column. What that means is that I can now put in each of these midpoints and the number of times it occurs, right? It saves me, obviously there is only one person who got a mark of 40. There are three people who got a mark of 50. That's the assumption we're making. We're going to use 50 as our best estimate. It saves me putting in 50, 50, 50. I can just say 50 and 3. Right, now just a little hint, when you put these in, when you press the kind of equals key on your calculator, all right, it actually goes down to the next number. Okay, so I'm actually going to put in all the sort of the x's. So I'm going to put 40, 50, 60, 70, 80, 90, 100. Again, be very mindful that you're putting these in correctly. 110, 120, and 130 is the last one. Okay, then I'm going to use the arrow key, and I'm going to go up to the top, and it's 1, 3, 4, 14, 10, 13, 12, 13, 7, and 3. Okay, at this stage I press all clear, which might seem like a very counterintuitive thing to do. But if I go shift stat, I can actually get back to my data. There it is. Okay. What I'm going to do first up here is I'm going to go shift stat, and I'm going to go for 4, the variables about this data. But I'm actually going to just check, have I got 80 data points? Oh, I have. Okay. Right. Now I'm going to go shift stat 4, and I'm going to get an estimate for the mean. All right, and it is only an estimate for the mean, and I get an answer of 90.5. Now, if they ask you to show some working, it's worth, just because obviously this might be worth like a few marks. You might want to write like one person got an average of 40. You might remember that there were 3 50s, so 3 times 50. Right, and you can see here, these are the bits of this formula, sigma being plus, 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 dot, 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 dot. If we go and look, there were, in fact, in the last group of 100, with a midpoint of 130, there were 3, so it'll be 3 times 130. Okay, and I'm going to divide all of that by 80. I'm not going to actually write it all down, but I get that final answer, which I got off my calculator now at 90.5. Right, the reason that it's an estimate and not an exact answer, okay, is because we don't have the actual data. Because we don't have the actual data, right? We're using the midpoints, all right? And by using the midpoints, we're basically making an assumption, right? That on average, the people in that group averaged out at the midpoint. It's kind of our best guess, right? It certainly makes more sense to use the midpoint than any other point. I think you would agree, right? And maths always makes sense. All right, onwards and upwards to question number 7. And here we've got 2 box and whisker plots. And the first question is, what's the median for class 1? Well, in fact, the median for both classes is actually 60. The interquartile range for class 2, really easy if you remember that your third quartile is the end of the box here, 80, and your first quartile is the start of the box, 80 minus 53, and 80 minus 53, 27. Okay. Describe the skewness or the symmetry of the data in both cases. Both of these are skewed to the right. Here, we are asked to justify why we've made that choice, and the reason being is that the data above the median spread, I'm sorry about my handwriting, cousin, more spread than the data below. Okay. Data below. Okay, now here's an interesting question. It says, what is P if 75% of the candidates in class 1 achieved a mark of greater than P? Now, the crucial thing with 75%, all this maths is connected to all the other maths, but 75% is actually 3/4. And remember, your quartiles divide the data into quarters. So in fact, we need to know, what is our first quartile for class 1? And our first quartile for class 1, all right, is 53. There it is over there. I'm hoping I've got that right. 51, 2, 3. It's actually 54. All right. And so the answer here is 54. Okay. And so 75% of the candidates in class 1 achieved a mark of greater than 54. Then which class has the greatest standard deviation? And this boils down to us understanding what standard deviation tells us. Standard deviation is a measure of how spread out the data is. And if we go look at these box and whisker plots, class 2, definitely more spread out. It will have a greater standard deviation. They're not asking us to calculate it. They're just testing that we understand what standard deviation is about. Okay, class 2 will have a greater standard deviation. And the reason being is that it's more spread out. Bigger standard deviation, more spread out, smaller standard deviation, less spread out. Okay, that was question number 7. A lot of these questions quite quick, which is why there seem to be a lot of them today. Question number 8, we're going to look at bivariate data. So we've now got a kind of a scatter plot thing here. All right, 13 students, we've got their AP maths marks and their maths marks. All right. And the question, we're not given the actual data. We're not asked to find the equation of the least squares regression. I'm just going to do some sort of interpretation stuff. The first thing is the question says, what's the nature and the strength of the relationship between the performance in these two subjects? Right? It's strong. Right? There's a strong relationship. And it's positive. Right? And what we, so I haven't left myself any space here, but what we mean by positive, all right, is that the line slopes uphill. And what that means is that a learner who does well in maths is likely to do well in AP maths as well. Right. So in other words, a more the more relationship as opposed to a more the less relationship. Okay. All right. The teacher plans to use the equation of the least squares regression line. So it has been calculated, it's been brought in to predict the AP maths score of a student who scored 30% for maths. So in other words, to sort of say, right, let's see where would this, if this line, if we kind of continued this line, and herein lies the kind of challenge, all right, what would the line predict about a maths mark of 30, all right? And this process that we are using here is what is dangerous, it's risky, it's what is called extrapolation, okay? Extra actually means outside of. I don't know if you know that, but extraordinary means out of the ordinary. Okay. Intra means within. Okay. Right. So when you have an intra-house event, it's actually a sports event. It would be an intra-school event is within the school. Inter is between. Okay. So inter would be between houses or between schools. But we're talking here about extrapolation. And the reason this is extrapolation is we are looking outside of our data. Our data is here. This is the range of our data. All right. And we're going outside. So it's risky. Okay. I'm not going to write it down. I haven't left myself enough space. Then it says one of these data points could be considered to be an outlier. Which one? Circle it. Okay. It's clearly that one. All right. And now it asks, what would be the effect if we removed that outlier? What would be the effect on the gradient? And also what would be the effect on the correlation coefficient? Well, the correlation coefficient is currently strong. It's heading towards 1. All right. Remember, 1 is a perfect correlation. This is maybe about 0.9 or something. It looks very high. All right. But in fact, it would get even stronger. So if we remove the data point, the correlation coefficient would increase. And in fact, it will increase and get closer to 1. Okay. We might even want to say it gets even closer to 1. Because it's already, sorry, it's running off the screen. Gets even closer to 1. What would happen to the gradient? Well, if we look at the gradient, we remove that, the line will actually tilt slightly higher up. The gradient will increase. Right. Onwards and upwards to question number 9. Now, this is an interesting question because it's really testing that you're able to work out a standard deviation without a calculator. Okay, so I'm going to go through it reasonably quickly. The first thing it says, get the mean. Right now, if we add all these things up, we actually get 1, 2, 3, 4p, and that's 2, 5, 7, 11. All right, and minus 3, it's actually 4 plus 8. And so if we divide that by 4, we actually get p plus 2. So the mean of this data set is p plus 2. All right, now we're going to determine the standard deviation in terms of p. Right, and in fact, what we're going to do, remember that formula is, I'm going to write the formula up here just to give myself a little bit more space. We get provided with this formula. This is a formula for variance. I'm not going to write in the I equals 1 to n, just xi minus x bar up to n, all right, over n. That will give us the variance. So what we're going to do now, we're going to take p plus 2 away from each data item. So the first one, we're going to get p plus 2 minus p plus 2, which is going to get 0, and we're going to square that. The next one, we're going to get p minus 3, and we're going to take away p plus 2, and we're going to square that. The next one, we're going to take p plus 5, and we're going to take away p plus 2. I'm going to do that one in my head, right? It's actually going to be no p's, and it's going to be 5 minus 2. It's just going to be 3. All right, we're going to square that. And the last one, p plus 4, take away p plus 2. We're just going to get 2. We get 2 squared. In fact, the p's go out of this middle one as well. And we end up actually with 38 and no p's over 4. Right. So remember, that's not our standard deviation. That is our variance. Okay. So the standard deviation is actually going to be the square root of 38 over 4. That comes to a roughly 3.08 to 2 decimal places as requested. Okay. Now, it says without doing any further calculations, give the standard deviation of these numbers. Now, if we look at the two sets of numbers, each of these numbers is actually 4 bigger than its corresponding number previously. So every number has had 4 added to it. Now, if you stop and think about that, we can have added a total of 16, but when we divide that out, it will come back to 4. In other words, we divide by 4. So what's going to happen is that each data item has gone up by 4, but the mean has also gone up by 4. And if we look at this little piece in our formula, all right, if this is increased by 4 and this is increased by 4, then the gap between them has not changed. Okay, so if you add a number to every every item in a data set or subtract a number, you're not changing the spread, all right? So sigma will be exactly the same. It will be 3,08. Now, next up, if you look at these numbers now, these ones are actually twice as big as each number. Have a look here. This last one was p plus 4. It's now become 2p plus 8. If you multiply every number by 2, right, the mean actually also doubles. And if you play around, you can see why that is the case. So what we get now, we get actually twice xi minus x bar, which is also doubled, all right, squared. And what we can do here, sorry, okay, twice xi minus twice the mean. This is just each data item. Now, if we take that 2 out, we actually get 2 squared xi minus x bar squared. And notice what's happened. We've actually ended up multiplying each data item by, so each of these gaps by 4. 4 being 2 squared. Okay. But remember, at the end, we're going to square root our answer, and that 4 will then revert back to a 2. Okay. So, in fact, what's going to happen is that our standard deviation will be twice as big. So if you multiply each number by 2, the standard deviation multiplies by 2. So our new standard deviation for this data set is going to be twice the old standard deviation, and 2 times 3,08 is actually 6,16. Okay, right. Onwards and upwards to question 10. Okay, we've got this data set here, which is ranked. We asked to find the standard deviation. Right, I'm actually not going to I will just quickly remind you, basically mode, I'm not going to do the entire thing, mode, 2 stat, 1 variable, and I just put in these numbers. Notice, it doesn't matter that I've got my frequency mode on, I can leave it on, each of these is just occurring once. Okay, put them all in, press all clear, shift, stat, 4 for the variables and 3, and I get my answer, and in this case it's 18,05. Right. Here I'm asked to draw a box and whisker. Right. So I need the position of the quartiles. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 plus 1. Remember, 15 plus 1 over 4, that's kind of our like magic number. All right. That comes to 4. So my quartiles are going to be the 4th data item, 1, 2, 3, 4. That's my first quartile, Q1. The 8th, 5, 6, 7, 8, that's the median or the second quartile, 9, 10, 11, 12, all right, and this is the 3rd quartile. So we can see my 5 number summary is going to be those 5 numbers. My box and whisker is kind of going to start at 19, right, about 19. The first quartile is going to be about 25. The next quartile is going to be exactly at 40, the median. The 3rd quartile is going to be at 62, somewhere over here. And the biggest, maximum number is at 72, somewhere over there. Okay, and I get a box and whisker that looks something like this. Right, the memo, the sort of neatly worked memo will be available later. All right, it asks for the interquartile range. Remember, interquartile range is just Q3 minus Q1, and that's just going to be 21. All right, that's 62 minus 25. It's nowhere near 21. It's actually it's 41. No, it's not 41. It's 37, I think. All right, 37. Okay, so I need to fix that as well. All right, then it asks about the skewness. Well, this is actually slightly skewed right. Skewed slightly to the right. Not very, but it is skewed slightly to the right. Okay, then that's the end of that question. And I do believe, yeah. little bit. And we move on to the next question. All right, to question 11. So here we've got a set of data items in ascending order. Again, what's the modal value, the most common value? Well, if we look through this, it's actually 5. There are 2 5s. I don't think there's any other number that occurs as many as 2 times. And then the interquartile range, once again, the 19 numbers. I know I'm repeating this, and we're doing quite a lot of them. 19 plus 1 over 4. All right, and that gives us 5. Remember that at this, so the quartiles will be in the 5th position, the 10th position, and the 15th position. All right, so in fact, Q1 is in the 5th position, and it comes up to 9. Q3 is in the 15th position, and it comes up to 81, and therefore my interquartile range, just 81 minus 9, 72. Remember, and I should have done an example like this, my apologies. If this came out to say 5,5, then we would go 1, 2, 3, 4, 5, 6, and we would average those 2 numbers. In other words, we get 9.5. Okay, right. Onwards and upwards to question 12. Okay, and so this question says, now, a data set has got that, all right, and that's the standard deviation. How many data items were there? All right. Now, remember, if that's the standard deviation, then I can easily get back to the variance. Because remember, the formula that I get given for variance is this. Xi minus x bar, all right, squared over n. Okay. And we're actually told that the top of this fraction is actually 300. We also told that the standard deviation is 5 root 2 over 2. So the variance will be 5 root 2 over 2 all squared. And when I square that out, I actually get 50 over 4. Right. And I know that 50 over 4 is what 300 over n must be. So 300 over n, right, using this formula here, 300 over n must equal 50 over 4, because I know the variance, having squared the standard deviation. And now I'm just solving for n in this little equation. Remember that if you've got 2 fractions equal, the top of the one times the bottom of the other is equal to the bottom of the one times the top of the other. So now I get 50n is 1200. And I divide both sides by 50, and I get that n is 24. So there are 24 data items. Okay, this question can only be done if you really deeply understand how standard deviation and variance are calculated. All right, question number 13 is just a little test on understanding strengths of correlations. Okay, and we've just got to match these. Okay, so plot 1 has got a kind of a reasonably weak, plot 1's got a positive, not very strong correlation. I'm going with 0.6. I've got to choose one of these 3. All right. Plot number 2 has got a stronger than 0.6, but negative correlation. So plot number 2, I'm going to go with 0.9. And plot number 3 is actually the least correlated, and I'm going to go with 0. Okay. Right. If you asked to kind of estimate a correlation coefficient, like in other words, in the absence of these numbers, there will be some latitude given. But if, for example, for this plot over here, you said, well, 0.4, definitely wrong, because it's definitely a negative correlation. This is the more the one, the less the other, right? Your correlation coefficient and your slope of your line of best fit always have the same sign. Okay, let's now look at an example. 2 teachers look at correlations, performance between 2 subjects, all right, and we asked to find the equation of the least squares regression line. I'm going to quickly do this on the calculator just to make sure that you know how to do it. This time I'm going to go mode 2, and I'm going to go for 2 variable sets. Notice that my answers, my line of best fit is going to be in the form a plus bx. We use mx plus c in South Africa. A plus bx is an Americanism. It's a pity that this calculator doesn't actually give us what we want in South Africa. But anyway, I'm going to put in all the math scores first. So I'm going to go 60, 69, 51, 62, 70, 63, 54, 65, 69, and 57. And then I'm going to zoot up with my arrow keys up to the first one, and I'm going to put in the geography scores. 67, 80, 63, 72, 79, 69, 60. Just be mindful, don't get tired and make a mistake. Go slowly, check that you've got them right, because this question's worth a few marks, and the last thing you want is to kind of get it wrong because you've keyed something in incorrectly. Okay, right. I hope I've got them all right. Okay, and now we go Shift Stat, and this time we go for option 5, which is what we call regression. And I've got 3 choices that I'm interested in here: A, B, and R. Remember, it's A plus BX. So I'm going to go 1 for my A value. All right, and I get 7,594. All right, and then I'm going to do the same thing again, but I'm going to go 2 for my B value, Shift Stat 5 for regression, 2 for my B value, and I get 1,026. Okay, these are the same numbers that I got when I did it earlier, so I'm quietly confident that it's right. But remember, it's A plus BX, or BX plus A, so 1,026 times by X plus my B value of 7,9, so my A value of 7,594, right, and there it is. Okay, then it says, and this is really important, show that the X mean, Y mean lies on that line. Okay, so what I'm going to do now is I'm going to go back to my calculator, and I'm going to get that X value, that X mean. Okay, sorry, screen again. Shift Stat, this time I'm going to go for 4, and you notice I can get my X mean and my Y mean. My X mean is actually 2, so let's get that. All right, the X mean is 62. Okay, so X bar equals 62. Right, now what I'm going to do is I'm going to use my line of best fit to kind of work this value out. 1,026 times 62 plus 7,594. Now I want to show you that your calculator can actually do this for you very nicely. Right, if we go and we go, now that answer's on screen. If I go Shift Stat 5 to my regression and I go for option 5, that's basically saying, give me the Y value for the X value that was on screen, and I get 71,2. Right, so the answer to this is 71,2. Right, now what I'm going to do is I'm going to get my calculator, I'm going to check what is the actual mean of the Y value. So I'm going to go Shift Stat 4 variables, and I'm going to get the mean of the Y values, 5, and lo and behold, I get 71,2. Right, Y bar equals 71,2. Right, this point always lies on the line of the best fit. Okay, then it says, comment on the nature of the relationship between the two data sets with reference to the correlation coefficient. So let's go and look up our correlation coefficient. So Shift Stat 5 for my regression, and I'm going to go for option 2, which is not 2, 3, which is my R value, my correlation coefficient, and I get 0.951. That is a very, very strong positive correlation. Okay, right. So it asks us to just sort of explain a little bit the nature of the relationship. So very strong positive relationship. And what that suggests is that the line slopes uphill, and I don't know why I'm anxious about whether you're seeing an uphill line when I'm not sure if it's inverting the image. Okay, but anyway, very strong positive relationship. And what that means is that the line's basically going to slope uphill. All right, if we're to sort of plot this thing, it's going to look something like this. All right, which suggests that someone who does better on the sort of X and maths is also likely to do better in geography. Right, so basically doing well in maths, likely to do well in geography. Obviously, you'll get outliers, but we're talking about on the sort of for most cases. Right. Now, these two teachers wish to use this least squares regression line to predict a geography result for a boy who got 45% for maths. And once again, if we look at these maths marks, the lowest maths mark here is actually this, as far as I can see, it's this one over here. All right. And 45 is below that. So once again, we're using, if we use our least squares regression line, if we use this line over here to make predictions outside, risky. Okay. All right. Comment on the possible reliability, risky. Even though the correlation is strong, we don't know if that pattern will be maintained. Okay. Risky, extrapolation. Right. And I just want to kind of give you a sort of a real life understanding of this. When basically, if you take people's sort of maybe their ages and their heights, all right, as they get older, they sort of get taller. Okay. And I'm talking about sort of maybe 1 to 5 year olds. Okay. And there might be a reasonable sort of linear relationship of some sort. It wouldn't be as strong as that. But as we know, so this is age on this axis, and this is height on this axis. That isn't maintained. We know that kind of 25-year-old or 19-year-olds and 70-year-olds actually are likely to be the same height. In fact, we even know that sometimes as people get older, so it's very risky to people might start getting slightly shorter as they get older. Right? It's very risky to make an assumption that this line is going to carry on doing that. It may well not do that. In the case of heights of people, it definitely doesn't do that. Okay, right. Onwards and upwards now to a cumulative frequency curve. All right, so here we've got a table with some data that's actually missing. All right, but remember the cumulative frequency, there are 4 instances between 4 fish between 0 and 10, 10 fish between 10 and 20. That 14 says that there are 14 fish kind of less than 20. Now, there's an additional 15 fish here, so this is going to jump up to 14 plus 15, 29. 29 plus 25 up to 54. Right, 54 becomes 74, and then what must have been here to get from 74 up to 86, and the answer is clearly 12. Okay, so we've filled in the table. Now, I'm not going to spend, okay, now ask us for an estimate of the mean. When we estimate the mean, we're going to use the midpoints, and we're going to use our group data. We're going to use our frequency mode on our calculator. I'm not going to do this calculation again. I'll tell you that the mean for the estimate for the mean comes out to around 39.6, and it's an estimate because we don't have the raw data. We're making an assumption that these 4 fish averaged out at 5 centimeters. We might be wrong, but it's a better guess than anything else. Okay, all right. And then we are asked to draw a cumulative frequency curve. Now, the crucial thing with this cumulative frequency curve is that we plot the end points against the cumulative frequency. So we don't use the midpoints now. We use the point 10, 4. We use the point 20, 14. That's our next point. We use the point 30. We don't use the midpoints for a cumulative frequency curve. 29. I'm not going to draw this accurately over here, but basically we also start off here at 0, 0. Okay, so it looks, I'm going to try and copy what I've got over here, and it looks something like this. What happens always with a cumulative frequency, all right, our last point here is actually 90, right? 90, 100. So the frequency curve ends up at the height. This is n. This is our total number of data points over here. Okay, and it's normally that sort of shape. Okay, that's not really very nicely drawn. If I wanted to estimate, and it doesn't ask us in this particular question, but if I wanted to estimate the interquartile range, well, the third quartile will be at 75 out of 100. And I would read off, and that would be my position of Q3. My first quartile would be at 25. I'd read off, and that would be more accurate, Q1, and then I would subtract it. Okay, we're coming to a question like that, so I'm not going to do that one. All right, I've been a little bit repetitive here. This is a very sort of general one, but again, it's the same principle as before. The mean of n numbers is m, and the standard deviation is s. Give the new mean in terms of m and s if 7 is added to each number. Well, the new mean will be m plus 7, but the new standard deviation will be s. Right. If each number is tripled, the mean will be tripled as well, and in fact, the standard deviation will be tripled. Okay, if you're not convinced, practice, put some numbers into your calculator and try tripling them all and get the standard deviation, and you'll see. Right, here's a cool sort of problem-solving question. So a teacher was looking at the correlation between maths and science results of 40 students. Unfortunately, she spilled tea on her working, leaving only the following information. We've got the slope of the least squares regression line. Okay, that's great. We've got the average of the maths marks. We've got the sum of the science marks, the total of the science marks. And we know that there are, in fact, 40 of them. We know that there are 40 of them from this. All right. We also know that there are 40 of them because it actually tells us over here. All right. So we can easily get the mean of the science marks. We can get y bar. Right. And y bar is going to be 2800 divided by 40. And 2800 divided by 40 is 70. Now, I know my equation of my least squares regression line is y equals a plus bx. All right? I don't know what a is. I do know that b is 0,841. But also, I know, and this is the crucial piece, this is the kind of aha moment, that x bar, y bar, lies on this line. So 67 as an x and 70 as a y must lie on here. If I substitute that point in, 67 for x, 70 for y, I can solve for a, and I get a is 13,653. Right, you cannot do that question if you don't know how to interpret sigma notation, and if you don't know that x bar, y bar, the centroid, always lies on the line of best fit, on the least squares regression line. Okay, right. So let's, I need to write the final equation down. So it's actually going to be 0,841 x plus 13,653. Right. Then it says, comment on the reliability of using this line to predict the science result of a student who scores 95% for maths. Now, the top maths mark was 89. Once again, problematic, potentially risky, because this is extrapolation. Risky, we are extrapolating. Okay, comment with justification on the correlation between the maths and the science results. Right. Well, what we've been told, if we go back and look at this data here, is that the correlation coefficient wasn't lost in the tea being spilled. 0,961. That is a very strong positive relationship. Very strong positive. Okay, very strong, right? Close to 1. I'm justifying why I'm saying very strong. All right, positive. Okay, positive because R is bigger than 0. But what that also means then is that success in maths, success in maths is likely to lead to success in science. Okay. Question number 18, which I think is our penultimate question, the second last one. All right. We've been given a cumulative frequency curve. How many students wrote the test? Well, remember what I just told you, that number there, 80. Use the curve to estimate the interquartile range, showing where you've taken off your readings. Now, 3/4 of 80 is actually 60, so we're going to kind of zoot along there. And we're going to read down here. Right? And 1/4 of 80 is actually 20, so we can zoot along there. Right? And we get this one, our Q3 looks to be about 72, and our Q1 about 64. So our interquartile range (72 minus 64), it's going to be 8. Okay. All right. And then it's decided to award a merit certificate to the top 12.5% of learners. Right. So basically, we want to know what is 12.5% of 80. Right. And that actually comes to 10. Okay. So we want to know kind of what mark does one need to achieve to be in the top 70 learners. Sorry, to be in the top, the last 10 learners, in other words, at the top end, right? And that we can easily read off over here. There's 80, so 70 is over here. So use a different color pen. And because this basically is 12.5% up here and 87.5%, the balance down there. And if we read off over here, it looks to be about 78% is the mark that one will need to get to qualify for a merit certificate. Okay. And then the very last question now is one I made up myself, and I'm rather proud of it. It's a kind of a problem-solving question, definitely, in standard deviation. So the 20 people in a room, their average age is 32, all right? And the standard deviation is 2√3. Now what happens is that two people leave the room, a 28-year-old and a 36-year-old. And what's the standard deviation of the people who are left behind? Right, and you might be surprised that you can work this out, okay? You can absolutely work it out, because if we, and again, I'm going to write down our formula for variance. Just going to use a different pen color. So our formula that we get provided on the formula sheet is this: xi minus x bar squared over n. Right, so we know the standard deviation of the people in the room. If you square that, right, this is the number of people in the room, these are all the people in the room initially, you actually get 12, right? And there were 20 people. So in other words, this piece of this formula okay, once you divide by 20, you get 12 as your answer. So in fact, this bit, just the sum, must be 240. Right. Now, the crucial thing that makes this question possible to do, right, is that the two people who leave don't affect the mean. And the reason being is that this person is 4 years older than the average age, right? Because, sorry, the average is 32, sorry. This person here is 4 years younger than the average age. And this person is 4 years older. So they don't, the mean doesn't change when they leave, all right? And you wouldn't be able to do this question if that wasn't the case. But what we are able to tell is how much did they contribute to this total of 240? Well, one of them, this one is 28 minus 32 is minus 4 squared. It's actually 16, all right? And the other one is also, it's actually positive 4 squared, it's also 16. So those two people actually contributed, the two people who left contributed 32 to this. The two who left 30 to the 240. So when they leave, that number comes down to 208. Right? But remember, we take that number, we divide by how many people are in the room, and now it's only 18. That's not our standard deviation, that's our variance. Right? So our new standard deviation is actually going to be the square root of 208 over 18. And it actually comes to about 3,399. Okay. So yeah, I think it's quite a cool question. Again, it really tests your understanding of how standard deviation is calculated. Okay, guys, and that brings us to the end of these live streams. They've been an enormous amount of fun for me. They've also been an enormous amount of work. I really hope they've been useful. I just want to wish you everything of the best. If you're watching these videos, don't just let the video play. Pause the video, check your own answer, or if you haven't tried the question, try the question and then let it run again. Okay. Yeah, all the best. God bless all of you. Okay. Cheers, guys. All the best. And please, I'd love your feedback, even if it's just to say, yeah, they helped, or no, they didn't help, or I would have been watching all the episodes of Friends, or whatever it is. Tell me if you've got any feedback for me. If you like the videos, if you enjoy them, then please like them on YouTube. But most of all, please tell your friends about